Gravity, like any other force, can exert a torque on a body. With this pair of pliers, one arm is a rigid body rotated around that hinge right there. And gravity, the force of gravity on that arm, can exert a torque, causing it to rotate about that point. So we would like to be able to compute that gravitational torque acting on this arm right here. To do that, we're going to need to first discuss how to find the center of mass of a rigid body. So a bit of review here. First, the center of mass of a discrete mass distribution. By a discrete mass distribution, I mean some collection of point masses. So here in this xy coordinate plane with an origin, I've got three masses, m1, m2, and m3, located at these three positions, and they could be three different masses. Let's say that the collection of them constitutes a system. And suppose the center of mass of the system is located there. Then these position vectors can be expressed in terms of our unit vectors. So the position of mass 1 is given as x1 I hat plus y1 j hat plus z1 k hat, where x1, y1, and z1 are the x, y, and z coordinates of this mass. Okay, and likewise for the other two masses. And then the position vector for the center of mass could be expressed in terms of the x coordinate of the center of mass, the y coordinate of the center of mass, and the z coordinate of the center of mass. The definition of the center of mass position vector is as the weighted average of the position vectors of each of the other objects, each of the objects in the system. So here's our definition. We take each position vector, R1, R2, R3, and weight it by the mass, and then sum those, and then divide by the total mass. You'll recognize this expression here as being related to these that we have derived previously. If we want the x-coordinate of the center of mass, we want the weighted average of the x-coordinates of all the masses. Likewise for the y-coordinate of the center of mass. So this expression just puts these two expressions plus the expression for the z-coordinate of the center of mass together into a single vector equation. All right, so restated, here it is, how to compute the position of the center of mass for some collection of capital N discrete point masses, a discrete mass distribution. The mass of the total system can be found, the total mass of the system can be found by summing up the masses of all n point masses in the system. Okay, so all that is to set up what we already know about a discrete mass distribution in order to contrast it with a continuous mass distribution. So a continuous mass distribution, this would be some body that takes up space and has volume, like this potato here. This potato takes up space, it has a center of mass somewhere, but it's a continuous distribution of mass. It's not just a collection of point masses. So this continuous distribution has a center of mass, and we would like to find its center of mass. And the way we do it is to sort of imagine dicing up this continuous mass distribution into a collection of an infinite number of infinitely small little chunks of mass. Trying to imagine this continuous mass distribution as if it were a collection of an infinite number of little discrete masses all packed closely together. So here I've shown three representative little chunks of mass, little cubes that are, we can imagine, vanishingly small, these three yellow cubes. And if they are infinitesimally small, then each one represents an infinitesimal amount of mass, so we call that mass dm. D as in a infinitesimally small amount. So the total mass of the system we can get by this integral here. The integral meaning we add up an infinite number of infinitely small things. Each little dm here is an infinitely small amount of mass. We add up an infinite number of them, and we'll get the total mass of our potato. Of our whole body. Now, each little piece of mass we can locate with its position vector. So if this particular little cube of mass, this little infinitesimal dm1 is located here at position vector r1, we can do the same with all the other little pieces of mass. And then define the location of the center of mass as the weighted average of all the position vectors pointing to every single little bit of mass in the whole body. So here is that idea expressed in equation form. The position vector of the center of mass can be defined as the weighted average here. So we'll take this mass, this tiny little mass here, dm1, times its position vector, and add that to this little mass, dm2, times its position vector, and then so on, and there will be an infinite number of these terms. And each term is infinitely small because each little dm is infinitely small. Okay, so if we're adding up an infinite number of infinitely small things, we are integrating. So the numerator can be concisely represented by this integral here. Integrating over the whole body, we'll take every little dm and multiply it by its position vector and add those all up. In our denominator, we're going to add up all the dm's. So if we're adding up an infinite number of infinitely small dm's, that's what this represents here, and we will get the total mass of the system, the total mass of our potato-like body here. That's our denominator. So there we have it. This represents, this equation allows us to compute the center of mass vector for a continuous mass distribution or a body. Now, this equation is a vector equation. We could also represent it as three separate equations, one for each direction. So the x-coordinate of the center of mass would be the x component of this equation. So we would be taking x dm in our numerator. That is the x-coordinate of each little dm times each dm and add all those up. Likewise for the y-coordinate of the center of mass and the z-coordinate of the center of mass. So every vector equation, such as this one here, which is this, every vector equation really represents three separate equations, one for each component.